the other course as well. I'm doing the 606 along with this course. So I feel like most of my time is spent just doing the homework rather than I mean, sometimes it helps, just like it's going through the textbook and just trying to get the homework done rather than trying to like spend some time really understanding the concepts and like what we're trying to accomplish.
Right. I think one thing is doing homework, right? The other thing is when you definitely need to read the book. But I just hope that I can guide you through better to go through the book because I can't read the book for you. So I just hope that the slides that I put on there would be somewhat useful. If it's not, or if you have any other questions, or you have something that you're interested in, just let me know, either through email or through Blackboard system.
Yeah, well, the slides are pretty much what's on the textbook. So sometimes I watch your videos too, but I think it will. I don't know the timing of when the assignment is due versus when the lessons gets posted. I guess. I think we need some time to like just go over some of the materials. So we can do it in office, I don't know, office hours or.
Oh, we can schedule
one-on-one before you tackle the homework.
But if you have any questions, we can schedule something together. Meaning that send me an email. I can let you know. Okay, maybe tomorrow night at 7 p.m. we can talk through Skype or something else, and then I can explain some of the concept to you as well. If that helps you, that can help you to study.
Yeah, this is Aaron. It would definitely helpful. I want to see what the rest of the class is. Yeah, this is yeah. So for me, I feel like I've been kind of going as fast as I can to get all the reading and homework done right now. So it hasn't left me a lot of time for posting questions or anything. But I think I'm starting to sort of get my feet under me, and I definitely have a couple. I've got a couple questions tonight on some of the homework. So I think that you'll get a little bit more response as we move along. But.
Okay. Okay, so today we actually have. So anyone have any other questions, or if not, I can just go ahead and move on.
Yeah, I believe as Aaron said, I don't know whether you are going to post the solution for homeworks other than grading them. Because I also have a couple of questions on the homework you posted and I submitted.
Yes, I'm going to prepare the solutions for you guys so that you guys can take a look. And another thing that I just briefly reviewed some of the homework. I didn't grade yet. I just want to take a look and get a sense. My suggestion is since we are using R in many other courses, if you could pick up the R in this course as well. For example, some of the fitting, of course you can do it in Excel as well. I'm not saying that you have to do it in R, but I just encourage you guys to do that in R because eventually as a statistician or as a data scientist, you have to use more advanced language such as R instead of Excel. In the real world, for statistician, I guess either R or SAS or S plus or SPSS, because it just has more capability, more functionality comparing to Excel itself. But it doesn't mean that you cannot use Excel. I think that's fine as well. I just see that as a statistician or data scientist, especially master level, eventually you probably would need to pick up one or the other statistical language. Okay, so if you don't have any other questions, so I'll just continue. I probably will go through chapter 2 rather briefly and then go to chapter 3 and 4. And And as I just said, the slides that I have here is more like introduction. I want to give you a direction to take a look at where you should pay attention to. That's all. So you probably have to do a lot of reading yourself. And if you have any questions, just ask me. Okay. So I'm going to mute everybody. If you have questions, just go ahead and ask through the chat window, or just jump in through the chat window. Okay, so this is for chapter. So this is for chapter 2. Chapter 2 is more fundamental to talk about modeling process, and it also discusses a little bit about proportionality and the geometric similarity. So I'm not going to go over the detailed examples in the book, but some of the examples are really, really useful because this is the first time I read this book. I found in general it's a good book. It has everything has theory, has application, has very good examples. That's why I encourage you to read the book. To be honest with you, I'm not that strict with homework per se. I still hope that you guys can do some reading to do the homework. The homework is only one way to gauge how much you understand the reading and the textbook. And actually, there's another thing. Today, San Diego sent me an email that reminded me that I didn't mention the homework late policy. So I'm going to send you guys an email regarding this. So because this is already the 3rd week, so I was saying that I'm going to give everybody 2 weeks, 2 homework late. That's okay. If you have 2 homework late, that's okay. But I prefer that you guys can send me an email or let me know somehow beforehand. For example, if on Sunday night, 11:50, you find you couldn't finish it, you're sure you definitely cannot make it, send me an email, that's okay. Even 2 days earlier, that's fine as well, because if your schedule is just too tight. So meaning that what I'm saying is for the whole semester, you can have 2 late submission, but try to let me know beforehand. And beyond 2, if you have 3rd or 4th or 5th, I can only count 70% of the grade that you actually get. But I'm going to send you guys an email on this so that everybody will be on the same page. Okay, continue with chapter 2. So this one, last time when we meet, we talked a little bit about here as well. So essentially, how can we use mathematical model to model a real-world system? So it has simplification, analysis, interpretation, and then we can use real-world system. If we don't have a math model go through this route, we could just try and get some real-world conclusions. But if we have some mathematical model, we can use real-world explanation or prediction and use real-world data to verify whether the model makes sense. As you can see in this process, it actually involves a lot of things, right? One thing is whether your model is a real good representation of the real-world data. That's one thing. The other thing is whether it's too good, it really fits the real-world data so well, but it just doesn't have any predictable capability, right? That's actually called overfitting, meaning you fitted your data too well, but you cannot extrapolate the model to other scenarios. We're going to cover in the whole course about these ideas, but here next page we probably see something about this as well. So the nature of the model here says, okay, one thing that I want to mention here is here we talked about something called simulation, right? Simulation is one way to simulate the real-world behavior. But what is mathematical model? Mathematical model is trying to build a math model to solve real-world problems. But simulation is to simulate the real world to answer some of the questions. So as you can imagine, actually, mathematical models, simulation usually would be used to simulate complex problems that you cannot model it as mathematical model in the sense that it's just too complicated to model. To use a math model, that's when you use simulation. But when you construct the model, as here says, okay, you have to consider flexibility, cost, or some other situation, whether you can get data, so on and so forth, right? So for different types of things, the real-world observation fidelity, it's real, but it probably, if you want to get those observations, its cost would be high, right? But flexibility-wise, if we really have a mathematical model, we can use it for different scenarios, for predictions. That's why from all these three perspectives, it has its own advantage. Okay, and then here it says, how can we construct a model? One thing, as you can imagine, think about what's the problem and then make some assumptions and then construct the model and then try to solve the model and then look at the real data to verify the model. Of course, no, not the verify the model yet, actually. Verify the model essentially saying that use your model, look at the original assumption or original problem and see whether your model actually makes sense. And then implement the model. Step 6, maintain the model actually goes along the line that we need to look at whether the model makes sense, whether it can be applied to real-world problems. And you can imagine it is an iterative nature, and you have to go back and forth, especially in some cases. The assumption could be wrong or could be inaccurate. So meaning that some of the cases that you can make some assumptions that's okay, but some of the cases you just can't. You can't because assumptions itself make modeling process easier. But if you don't have the right assumption, it make your model doing the wrong thing. That's essentially the idea here. So here it's the same thing. Models, in the model simplification side, you try to neglect some variables, restrict problem identification, so on and so forth. But you have to consider those additional variables when you find your assumptions really do not make any sense. Here is like linear proportion. I'm sure you guys already know this because you have already worked on the homework too. And we're going to discuss how to fit a linear model next chapter, which would be covered today as well. And many of the law and all this you have learned in high school already, even also, of course, in college as well. Just to give you some examples, it's some mathematical abstraction of what you have already known. Yes, actually, they here a very good case, as I said, chapter 2.4 and 2.5. And I hope that we can discuss more on this as well. If you have any questions, we can discuss. That's homework 2. Okay. Yes, go ahead.
Yeah, you skimmed over that geometric similarity.
Yes.
I found that kind of an interesting way to do things. How often do you really do that versus sort of try to? I guess it seems like you can spend a lot of time trying to go through geometric similarity and figure out whether or not you've got like an x squared or an x cubed relationship, or you can just sort of fit a couple different, polynomials of different orders and see which one fits better.
Right.
Is there, do you have one, is there a preferred method or one that just happens more often?
Okay, so hold on. Let me mute you guys first. Okay. So for this question, essentially you're asking if there is a systematic way to fit the model, right? It's either linear or nonlinear or quadratic, polynomial. Where should we start, right? So usually what you do is you look at your data and try to look at how good linear fit would be a possibility, whether linear fit would be a possibility, and whether the relationship between y and x is linear or not. If it's not linear, then you start thinking about other models. But the thing is, you don't want your model to be too complicated. For example, if you fit y equal to x powered by 8 plus b times x powered by 7, so on and so forth, definitely you can get a better fit in terms of modeling perspective, right? But the problem is your model could be too complicated in our case. And also it doesn't have predictability, meaning it fitted your data so well that it doesn't have capability of go beyond your data. So essentially, what I'm saying is we want to have a model that's good enough to capture all the variation of the data. Meanwhile, you don't want it to be too complicated. So does that answer your question?
Yeah, I guess I understand how using lower order polynomials gives you a less complicated model and probably helps with overfitting. It seemed like they spent a lot of time in the book, though, talking about geometric relationships and really getting into what, like, you went through the physics of something to figure out whether or not it should be, velocity squared versus that you're comparing braking distance to, or just velocity. Whereas if you just took the data and fit velocity and velocity squared and velocity cubed, you would have you could get kind of an idea of which one fit better. I was wondering if there's a preferred a technique that's really used a lot, where you go through the actual physics of the thing to create your model, or if you just sort of start throwing equations at it, if that makes sense.
Okay. So one thing is linear model. First of all, actually, I want to show you this page. So ladder of powers. This. Hold on. Let me mute all first. So essentially, so we're trying to. Sometimes because linear model is better to. It's easier to fit in general. So that's why sometimes if it's nonlinear, we try to do some variable transformation and then to model the problem. This is a ladder of powers, meaning that usually it's better to start with some of this transformation. I hope this is helpful. Although your question is more along the line of it really doesn't have a systematic way. It's more like you have to look at your data and visualize to see which model might be better fit. That's all. You can try maybe a couple of them and then pick the best one. That's all. And then how to pick the best one? We have some rules or some error checking mechanism as well in the course we are going to discuss. Does this answer your question?
Yeah.
Okay. Okay, so let's continue for chapter 3, model fitting. So first of all, say here how to fit the model to data graphically. This is also very much similar to what you have learned in chapter 2. And then in chapter 3 also studied analytical method of model fitting and how to apply the least square criteria so that you can choose the best model. Okay, a couple of problems when we try to do the model fitting. One is the fitting a selected model type or types to the data. So the precise meaning of a best model must be identified. So how do you see that you find the best model? Why do you think this model is better than the other one? This fit is better than the other one. And the other thing is choosing the most appropriate model for competing types that have been fitted. So that meaning that we have to set up some type of criteria and making predictions. And determine how to make the predictions. That's what it is saying. And here it says sources of error in the modeling process, including formulation error, meaning that just formula is not correct, truncation error because of some truncation of the data or truncation of the pieces of submodels or pieces of data. There's some errors, and also runoff error and measurement error as well. Visual fitting has potential problems, so sometimes we have to do some type of data transformation as well. So let's take a look at this. Here I didn't put the slides in here, but actually I want to go there so that we can take a look. 3.2. Okay. So here, this problem essentially says that if I want to, okay, the line segment AC is divided into two segments, which is AB and BC. And then okay, so essentially what we are trying to do here is to maximize this problem. And then let's take a look at how it was done. Okay, suppose x1, not sure if you guys can see, let me zoom in so that, yes. So essentially this is, okay, let's say, let x1 represent the true value of the length of the segment AB, and x2 is BC, so that there is some relationship here. One is x1 minus 13 equals to R1. x1 minus 13 equals to the distance from A to x1. And then x2 minus 7 is R2, segments of BC. Right, and then also x1 plus x2 minus 19 equal to I3. R3, which is AC, and then we try to minimize this R, which R is defined as absolute value of R1, R2, R3. You probably have to go through this yourself. And then subject to these three constraints, which is the first one, it has to be less than R. The total R is the largest number of those three. So this is, as you can see, this how we can transform a mathematical problem to a math programming problem, linear optimization problem. And then further, it was transformed to this form. And then this goes back to what we discussed in the first class regarding linear programming. So that why do we want to do this? You probably want to ask, why do we need this? Because there is a systematic way, which is called simplex method, to solve this particular types of problem. And then it turns out to be x1, x1, x2, and r to find where to find the best value that can maximize this function. That's the idea of this example. I think you guys should definitely take a look. And also another thing says the follow-up example is minimizing the sum of the absolute deviations of from yi to the function itself and absolute value and sum them up. So this is just brief overview of the problem, but what I want to explain is actually here. And then it turns out to be how to minimize that error, which is sum of squares of the error. How to define the error? Y is the model, Y is the predicted from, so suppose let's take a look if I have that equation somewhere. It's not here.
I'm muted.
Quick question for you.
Go ahead.
In the example that you just looked at, it talked about the simplex method. It seems like on the homework problem for that section, we're kind of implementing the simplex method because it asks us to solve that system.
For this chapter, it's no.
What's that?
For this chapter, we actually haven't learned a simplex method yet. So I don't think we need to use it in this chapter.
But on problem 2a, it asks, on problem 2, it says if a computer is available, solve for the estimates of A and B, which is...
Yeah, but this is not simplex. This is actually linear regression.
Okay.
Okay, I see what you mean here. But it's not simplex here yet.
So we don't use the simplex method to solve for that?
No, not for this problem. Not for this problem. But we can discuss more about this maybe through Graph system when you actually start working on it.
Because I thought that the way it's worded, I thought that when it says find the largest deviation, I thought that was the first method, right? I mean, it goes over the three different ways to fit data. The first one is the largest. The first one that you went over minimizes the largest deviation. The second one minimizes the sum of the absolute deviations, and then the fitting of squares minimizes the sum of squares of the deviation, right?
Yes.
So it seems like you can't just use a standard linear model to fit y equals ax plus b, because that pretty much minimizes the sum of squares, right? So are
Yes.
you're asking to do the Chebyshev method.
Right. So, but this minimized largest deviation should be able. I mean, the example that's in 3.12 should help you to answer this question.
Okay.
It didn't use method.
They didn't when they solved for x1 and x2, they just said, in the preceding line segment example, the simplex method yields a minimum value of r equals 1/3, x1 equals 12 2/3, and x2 equals 6 2/3, right?
Let me see. Okay, maybe you are right. If you have problems with that, actually I can point you guys to the right direction where to find that method. Right. Okay. So, for example, if we do that, I'm assuming that you're going to use R. So here, optimize simplex helps you, right? Of course, you have to understand how to read R package. But essentially, I can provide you some examples to how to use simplex in R, and then you guys can be easier for you guys too. Maybe this package sounds more promising. Looks like more promising, that's what I'm saying. Yeah.
Great.
Okay. In Excel, it has a solver as well that can help as well. But you have to set up the problem first, just as here. Okay.
Okay. Thank you.
Yep. Okay. Least squared criteria essentially is the sum of squares of the error, predicted value minus actual value squared, and then sum them up. That's the objective. For linear regression, essentially that is the objective as well. So how to fit a straight line? It is a linear regression problem. Formulates the linear squares. That is to say, the objective is y minus y predict minus y observation squared, and then sum up, minimize that value, and then subject to some of the constraints in the linear. But in linear regression, actually, there is no other constraint, but it could be non-positive. For example, xi is larger than equal to 0, y has to be in some area or something. But in general, that's what is linear regression, what a linear regression is. And then in order to solve that, you can hold on. Sure, let me finish this piece and then we can look at that question. And then take the partial derivative and then set the partial derivatives to 0 and then solve for the slope and intercept. And then for nonlinear programming, nonlinear regression, essentially you can fit a power curve. It could be cubic line, could be powered by 4, powered by 5, so on and so forth. And then sometimes we need to do the transformation from nonlinear to linear. The transformation ladder that I showed you that discussed a little bit in chapter 4 can help you to choose which transformation should be applied first. And then also how to fit the best model, look at the error, and also we have to consider the complexity of the model. It cannot be too complex, as I mentioned earlier, and it cannot fit the actual model too well, have an overfitting problem, but it doesn't have the generalization of the model, meaning it doesn't have too much capability of in terms of prediction. This is a homework for chapter 3. Go ahead, Shra. What's your question?
Hello.
Yes, go ahead.
Oh, yeah, I had a question on the phase 120. I just did not understand the inequality that it derived. Just wanted to understand what it meant.
120.
Is less than or equal to Cmax is less than or equal to Vmax.
120?
On page 120.
Here,
Yeah,
okay.
okay. Yeah, this whole thing. What is the relationship? That's
Yeah, I need to take a look at this book. I mean, this page, because I read this book a while back in the summer. Okay, by briefly looking at this, the idea is because each individual D1 is less than C1, if my understanding is correct, because okay, so this is true, right? Because every single CI is less than Cmax. So that this is less than or equal to Cmax squared plus Cmax squared plus Cmax squared, which is M number of Cmax squared. Does this make sense?
yes.
Because C1 is less than Cmax, so that C1 squared is less than equal to Cmax squared. C2 squared is less than Cmax squared, so that the whole equation is less than equal to Cmax squared plus and M number of those Cmax squared, so that this one is less than equal to M times Cmax squared.
So wait, why is the DI smaller than CIs?
I was wrong. That was not correct. That was not correct. Actually, I was saying that initially I thought that was the relationship, but it's not. Here it's only applying this Ci less than equal to Cmax. If I'm not making too much sense, let me explain again.
So Sharad, are you asking why the D is less than Cmax?
Well, I was just trying to understand what the relationship between these two methods were, but I was trying to follow it. Yeah. So the thing that threw me off was this special significance of the latter as previously discussed. I was trying to understand that. I mean, this one follows from. That's the only part that I didn't make sense to me.
Which one?
So because of the special significance of the latter as previously discussed, so it's clearly stating that at this point Dmax is at least as large as Cmax, because so that's the only part. Like, so what is that spatial significance that makes it so? Because after that it makes sense. Yeah. So you have the inequality holds because you're multiplying times the maximum number.
Right.
So, and then you just follow it.
Yeah.
But yeah, what's the special significance here? That's the part I think I lost somewhere, so I didn't quite get that part.
Oh, so you're saying this special significance.
Yeah, so what is the Dmax, the relationship between Dmax and Cmax? So is it because of the absolute thing? I'm sorry, go ahead, somebody else?
Yeah. It's the two different methods, right? We talked about, like, the Dmax is that's minimizing the sum of the square distance, and the Cmax is that first method where you actually minimize the absolute distance. So that's why the sum of square to get that Cmax, that's the whole point of that method, is to minimize the the largest distance. So you get a minimal largest distance. So it has to be, by the definition of the method, it has to be less than your sum of squares. Or it can't be greater than, none of the sum of squares distances can be greater than that Cmax.
Yeah, I see what you're getting at, Aaron. The thing is, if there's two strategies, is it guaranteed to always give you the same line? In that sense, it would make sense, but why couldn't it be different?
The distances would be different, but you're saying equality that you're never going to have any of those distances on the, when you minimize using, when you get the best fit using sum of squares, you're never going to get one of those larger than
Yeah, let me take a look after the session about this. Hopefully I can get a better answer on this. My sense is what Aaron just said is probably correct.
Yeah,
but I just need to take a closer look.
Yeah.
Okay. So let's continue with this piece. Here, it's more examples here, but let's look at the next page. Actually, this is something that we want to discuss. So essentially saying that if this is a real world observation, right, and then we know that model C would be a better fit, but whether we want to pick this model or B, that's the problem that we usually face. Okay, and then the transformation, how to transform nonlinear data to linear data, essentially meaning that for the dependent variables, if you use y squared instead of z squared instead of z itself, it sometimes makes a difference to transform. After you do the transformation, a linear model might be fit instead of a nonlinear model. So here shows relative effects of different transformations. If we replace y equal to x, or y value is replaced by square root of y, how the model form, how does the model look like? And also higher or Lagrange form of the polynomial. This is not that useful here. I don't see how useful it is, but in general, it's something that you probably want to take a look. Again, we talked about here earlier, error, complexity, overfitting, and generalization. And then see, here, if it's low order of polynomials, error can be worse. But the model itself is simple. It doesn't have too much overfitting problem, and generalization, it could be increased. So meaning that we don't really want the model to be too complicated. I'm not sure if you guys understand what is overfitting and what is generalization, but if you have questions, we can discuss that after a couple of slides. And then continue with all this. How can we fit a better model? It could be a piece. This is called piecewise linear, meaning that the whole function is separated into different pieces. And then this is just a third order cubic line to fit that model. So it depends on, so if, for example, if we have some observations here, somewhere here, a couple of them, then could help us to determine which model might be better. If we only have these 3 points, it's really hard to argue which model is better. That's the homework for this chapter, but in general, you guys got the ideas. Still here, from first chapter to chapter 4, that's not the core of this course. What's actually we will be teaching is more on the linear programming and nonlinear programming, so on and so forth. Of course, some other topics here in the book as well. So as I said, do you know what is overfitting and what is generalization?
Yeah, so I guess if I had to take a crack at it, I would say that overfitting is when your model very accurately represents your data, then you run the risk of overfitting, because when you generalize your model, then it doesn't necessarily extrapolate very well, or if you take different sets, collect different sets of data, it may not fit those well too.
That's exactly correct. Okay, so let's take a look at this. So what is overfitting? So here it's a very good example here. If we look at this, all the observations, 1, 2, all these observations, right? We could fit a really nonlinear model to it. We fit the model perfectly. But the reality is, if we have an observation here, somewhere here, then the model doesn't do as well as the linear model, right? So that's the idea. We don't really want our model to be too complicated and also overfitting the data. So that's why in machine learning, actually, there is a concept called regularization, which is beyond what we're discussing here, but later on in your curriculum, you would learn this. So essentially meaning there is a trade-off between model fitting and model complexity and how good the model is, and then we try to find some location here that kind of balance between the complexity and generalization. It's called regularization in general. That's the idea. So you guys have any other questions? I think you have to read the book. That's why I said it probably helps if you read books beforehand, so that we can discuss a little bit more. Of course, I need to read the book as well. I read the book a while back.
I have a quick question on one of the homework problems. It says to estimate it graphically.
Yep.
Does that mean it wants us to basically just sort of eyeball it and say it's about this?
Yeah.
Or okay.
Yeah. At this stage, we're doing that. Yes.
Okay.
Any other questions? No? Okay. Yes, as I said, if you have questions, send me an email or discuss through Blackboard system. We probably need, because the first week, what happened was that because of the delay of the first homework, we kind of lag behind. Let's do that a little bit quicker this time around. Starting from the 4th week, 5th week, let's do something like at the beginning, on Monday morning, I'm going to post the questions on the discussion questions for the week, and then if you guys can start reading by the odd week. Yes, yeah, by the odd week of Thursdays, for example, from Monday until today, you already did some reading, and then we can discuss a little bit more about the details of some of the cases. Actually, it might be helpful if you have some specific questions. You can send me email. You say that I have some questions. You can send that question to everybody if you want to. I'm not sure if you are able to do that. If you do, you can send to everybody, and then anybody can chime in. I can read the question more carefully and try to get an answer to you in the session or after the session. So have any other questions, you guys? No? Also, another thing is if you have any suggestions on my session, that I need to improve, I can do that as well. And because I just started coming from a background previously in academia, but I have never been a professor in school. It's that's why I right out of after my PhD, I started working in industry. So teaching is something that definitely something that I need to learn as well. And I just hope that I can help you to study. That's all. And hope you can feel that you learn something from the course. That's my major objective. Okay, go ahead.
Hi, Sharad again. See, what I found really helpful with some of the other courses too, and some of the other previous instructor have been using is I supplement the so I actually watch those lectures.
Hold on, we actually just lost you. Can you speak? Say that again.
Yeah, what I was saying was I supplement my lessons with videos, sometimes on YouTube or sometimes on iTunes University. And if you send post us the links of some of the relevant topics, that will be very helpful. Right now I'm Googling it. And, like for instance, for the probability right now, I'm following some classes. So I found it very helpful, yeah.
So essentially you're saying that if I can, if the slides can be more detailed to explain the concept of
The slides are fine. The slides are fine. If you find some like videos on a certain topic, let's say, yeah, linear regression or like the fitting up.
Okay, I got it. So maybe I can send you guys every week. Hopefully, I can point you guys to some directions. Yeah, not necessarily every week, but sometimes if I think that's useful, I found something interesting, especially it's relevant to the course, the specific week, I can post those. Definitely, that's helpful. That's a good suggestion.
One thing that I liked that Professor Geary did last semester was he worked some pretty detailed examples during these office hours, and that was sometimes very helpful too.
So some professors actually have office hours?
Yes, but even so, even in these every 2-week meetups, he would go over some just very deep, like he would work some detailed examples, and we would go through some code and that kind of thing. So seeing some of these concepts implemented is always very helpful.
Yes, I think that definitely was that's what I said. I probably should find some examples in R regarding some of the implementation for this, because in this book it's a math-oriented course in the sense that this particular book is more like a math course. They don't really teach a lot of implementation here, but for some of the questions, in order to find a better way to solve the problem, such as I mentioned earlier, if we use R, it would be helpful. That way I can find some useful code or implementation of the model that can help you guys as well. I agree. I'll try to do that. So any other suggestions or questions here? No? Okay. If not, we can just stop here today, and we'll be in touch through emails, and let me know if you have any questions. We can schedule specific sessions, I mean individual sessions if you need. I don't want you to say that you're trying to do that all by yourself. I'm trying to help in some regard. So for example, very specific questions we can definitely discuss together. Okay. If you don't have any other questions, let's stop here, and I'll see you in 2 weeks. I'm going to be more actively talking to you guys through email and everything. Good night.